Hello everyone, thank you for coming, and we are ready to start. So today we have our special guest Géraldine Haack, who is a professor of GAP department here at Geneva University, and also she is co-founder of the Quantum Center, again here in Geneva, and she is going to talk about quantum thermodynamics. But before that, I will give a brief warm-up talk. And here I'm trying to show that actually the phenomenon, which we know from most of the courses about quantum physics, actually entanglement, is not super known yet, and also try to show you how we can represent density matrix and how we can guess is it entangled or not, and if we can do it in general. So let's start. And yeah, the first question that probably we don't really know what is entanglement. And the brief overview about quantum mechanics formulations that we can describe our system by vectors or by density matrices, and vectors they can describe only pure states, and density matrices they can describe pure and mixed states. And here you have formula for density matrix, and if the state is pure, then C is 1, and we have just one possibility, so it's not actually a sum, but just one product of cat and brown. Next, you can consider density matrix and its properties. Let's do it this way. Density properties of the density matrix. So it should be Hermitian, it should be semi-positive. It means that eigenvalues should be positive or 0. And then the trace of the density matrix is 1, and the trace of the square of the density matrix is equal or less than 1. And it's equal 1 if we're talking about the pure state. Otherwise, it's mixed. So we can apply this formalism also for many body or like 2 or more body system. For example, we can describe AB. And there a very useful notion which we are going to consider today, it's partial trace. So if we want to get the density matrix of subsystem, let's say A, we can take the trace, partial trace of the whole system and the subtrace of system B. And mathematically it can be described in this way, maybe more intuitive, if we have density matrix of the whole system of our two-body region in this way, so it's 4 by 4 matrix, and if we take the partial trace, then in the end we have sum of all diagonal elements of every block here, so A plus F, C plus H, E plus N, and K plus P. So that's, I guess, quite an intuitive notion. Now we can consider the ideal case when we just have 2 by 2 matrix, and we have 4 by 4 matrix and 2 parses, and they want to communicate in between each other. And from all quantum computing course or just quantum information course, you know that they can be entangled in very easy way. So we have Hadamard gate, which is actually can be replaced by this matrix, and if you apply it for 0 state, then it's C0 gate, which act on 2 qubits here and here together, and represented by this matrix. And for example, if we apply Hadamard gate on the 0 state, we get plus, and plus is just superposition of 0 and 1, so it's somewhere here. And in the end we have plus, and actually we check if we have 0 state, then we don't change the state of this qubit, or if we have 1 state, we change the state of this qubit. So in the end we get 5 plus Bell state, and Alice and Bob they're entangled, perfectly entangled, and we know how to do it. But in real case, we are given something like this, and it's a very useful way to represent the density matrix. So here you have all possible 4 states which you can have in density matrix, here as well. And here you can actually plot what you have. So for example, here it's 0.5, and we see that gray lines, they actually show the theory predictions. And we assume that in the center, we should have all 4 bulks equal to 0.5. So in experiment, it's a bit different, and read a simulation, but yeah, actually by experiment we are given these 5 and some small parts here. So if we're just given experimental density matrix without any theoretical knowledge, then it's quite difficult to guess are they entangled or not. So here from theory we would guess that we have a GEG, so GEGE, 0.5, EG 0.5, and the crossing 0.5. So obviously it's this state. But if you don't know it, then it's quite complicated. And the only teaching, I guess, so what is done in most of the courses, that the criteria you can use that entanglement is a state which is not separable. So it's not kind of a good definition. So here you can say that we know what is separable state, and everything what is not separable, it's entangled. But you cannot usually tell very easily if the state is separable or not. So here we actually don't know the answer on these questions. And we have some criteria which actually allow us to get some knowledge about it. And here, in this article which is mentioned here, you can try to go through proofs directly there. But we have one criterion from Peres-Horodeccy that actually shows us that if we take the partial trace of our density matrix, so we are going to know the density matrix of our subsystem, and if all the eigenvalues of them are positive, then probably we have separable state. So it's necessary condition for all dimensions, and also it's a sufficient conditions for n equals 4 and n equals 6. So that's what is proven, but maybe someone of you can prove that for other n it's true as well, but it's not known yet. And one of criterion which can be applied for our system to show that it's entangled or not, called negativity. And actually we consider the density matrix made by the partial trace of the whole density matrix, take its eigenvalues, sum them, and take -1. And if we get real density matrix, that we know that sum of all eigenvalues should be equal to 1, and then 1 minus 1 is 0, so for separable state it's 0 from Peres-Horodeccy criterion. But if it's different, then this one would be smaller than 1, and we get something smaller than 1. So this is one possibility to find something about our system and about its entangled. And also the second quantity which we are going to consider today is concurrence. It's a bit difficult mathematically, but let's try to go through it. And this criteria is applied only for 4x4 matrices, so we can consider only two systems, like two qubits, two-dimensional systems. And the first formula is quite easy. So we should take maximal from the following two quantities. It's 0 or the sequence of eigenvectors of particular density matrix, where A1 is the biggest one, and then all others we just take minus sign between them and then consider this sum. And the matrix which we consider is actually the matrix which we're interested in as a square root, and square root is defined just like this, so we get it's any matrix row which fulfill this criterion that square root times square root is actually the density matrix itself. And here we have also different density matrix which is defined by this formula. So here we have row which is just conjugated matrix, and the flip matrix here denoted by 4 non-zero elements. So this matrix is actually needed for stability of our eigenvectors AE, so that's why it's quite complicated formula, but you can imagine that it's just eigenvalues of the matrix which we consider more or less. And finally, so this is concurrence, and that's what we care about, but also there is one quite useful quantity as well. It's entanglement of formation, and it's defined as Shannon entropy of this quantity. And Shannon entropy, just to remind you, is just almost the classical entropy, but written in this value. Okay, and here, instead of x, we have the quantity dependence of independence of concurrence. And now we are going to compare concurrence and negativity, which is we defined in the previous slide. So here we have two plots, and actually we measure different conditions. Like here we measure entropy of formation, and here we measure negativity, the average value, and independence on R. And R actually is showing how mixed our state is. You can see that trace here of row in bar of 2, you know that this quantity is always less or equal to 0. So for fully mixed state, if we have 4x4 matrix, the maximum value is 4. You can easily check it. But if it's not, then, for example, for pure state, it should be 1. So we consider a range from 1 to 4, where 1 is a pure state, and 4 is completely mixed state. And from here you can see that here we have agreement in between two quantities. So if our R is higher than 3, then we actually don't have entangled state anymore. So our state is so mixed that it cannot be entangled. And on another plot, what we actually can see that our negativity is always smaller than concurrence. So here I guess multiple density matrix was taken, just random matrices around 100,000. And for all of them, concurrence and negativity were measured and compared. So here we have plot concurrence versus negativity. And we can see that for some of them, they're actually equal, but for others, concurrence is always higher than negativity. And it was proven also that for all pure states, concurrence equal to negativity. So that's how we can compare them, and that's the most usable criterion which I use now. And negativity, again, is defined for higher dimensions as well, but concurrence, no, still just 4x4 matrices. Okay, and now I guess you're already quite tired with these big formulas, but maybe we can consider higher dimensional systems. And for Peres-Horodeccy criterion, we've seen that it works for n equals 6. So we consider something with 6. So again, we have Alice and Bob, but we can add some other actors. And I'm pretty sure that members of the quantum club want to go there. So we have Alexandra, we have Elliot, we have Stefano, and I would like to join myself as well. So now we are 6, but now we need experimenter. And I assume that Geraldine would like to take this role. So here we have 7 of us, and we share the density matrix. So actually, we all together now have the common state, and from this common state we want to guess are we entangled or not. But actually we don't have a real criterion, but we can measure our states. And from here, what we can get actually something as following. So assume that we have the following experiment. We have 2 pairs of qubits, and from here we can produce the ladder of photons. So these 2 qubits, they produce photons, and they can entangle them like by pairs, or just all together in square, or just by pairs, or not entangled at all. This experiment was actually done by Alexander Grigoryev in QDEF lab this year, and it was presented in the March meetings, so it's quite new. And let's assume that all of our actors, they're not entangled at all. So these qubits, they just send photons and do not entangle them. So the density matrix, which we can have here, we have 6 states. So the number of possible states in 2 in the power of 6 is 64. So that's what we get. And we know that all the states here, all the states, they have same probability to appear. That's why we have on the diagonal the number which is equal 1 divided by 64, which is approximately 0.050. But now what happens if we entangle our qubits? So for example, entangle just 2 of them, then we are going to have already different picture. If you are interested, I can show you how we can entangle those qubits. It's a bit special procedure, but in the end, when you entangle it, you assume that if you have excited plus excited state of these 2 qubits, then you get additional minus sign. So that's why on 1/4 you have actually minus sign in real part of the density matrix. Later, and here on this plot is also very important that on the right corner you have theoretical predictions, and here you have actual experiment when the qubits were measured. And if we have more complicated entangled scheme, then the picture of the density matrix is already more complicated. We can go further, and then it is super complicated density matrix. And here we know how they were entangled, but for example, let's say that we have just this density matrix and we don't know what was made with these qubits. So actually from this density matrix, it's really hard to represent and get some information about entanglement. That's why for now, for all the experiments, these questions are very difficult, and I guess nowadays they're solved differently for different models, different theories, and different experiments. So that's quite a hot topic now, and new criteria and new proofs are needed. So that's all from my side, and the next talk is given by Geraldine, and we can send Entangled photon to there, and the topic is quantum thermodynamics.
So, good evening, and thank you very much for the invitation. It's really a pleasure to be here. Last time I gave a talk here, it was for my PhD defense. So, Anna, thank you very much for your introduction. And you said I will talk about quantum thermodynamics, but in fact the topic is a bit more specific. No, it's about quantum information in quantum thermal machines. So, indeed, I will talk a lot about entangled states, no, and how to manipulate quantum information resources. So mostly entangled states, but how to do that in the context of quantum thermal machines, and I will motivate this question. So the idea is how to combine the physics and all what we could exploit, understanding the functioning of a steam engine, and combining with like the most recent platforms for quantum computing. And so we are not so many, no? So I think just interrupt if you have questions, no, it will be more interesting. Yes. So this is the outline, no? So first I will review some of the ways that we know to generate quantum information resources, namely entangled state. So Anna briefly recalled this was called the ideal case, no, in your talk, where you can apply a C0 gate. But so that's just one way that I will also a bit re-explain, but I can go fast now. And so how to manipulate and generate quantum information resources. But then I will tell you a bit how to consider this very modern quantum devices as quantum thermal machines and why it is interesting to have this point of view. And finally, I will present you the functioning of what we call an entanglement engine, so which is a machine that is able to create quantum correlations. So let us start. So the first part is about manipulating and generating, entangled states. So, as Anna said, if you consider two parties, so entanglement is a notion that you can discuss with at least two parties. If you have two parties, A and B, I consider A and B to be qubits. So qubits are two-level systems. And just to set the notation, I will label the two energy states 0 and 1. And so there is a Hilbert space of A is spanned by these two states, and Hilbert space for qubit B is spanned by these two states. Now, these two systems can be in a separable state or entangled state. And as Anna nicely explained, is that in general, a state is said to be separable if you can write the state for the two parties, so for the total system, as a tensor product of the state of system A and the state of system B. And this is not possible for entangled states, okay? So just to give one example, if my two qubits are in their ground state, so both have excitation there, then I can write, you see, so rho is my density operator, but this is the same notation as Anna used. So if my two qubits are in their ground state, you see A is in its ground state, so that's the projector onto the ground state, and B is also in the ground state, and this is a convention or a notation, instead of writing each time the tensor product, one just write the ket for qubit A, qubit B, qubit A, qubit B, okay? But for an entangled state, it's not possible. And one example that I will speak about during this talk is, for instance, the phi plus Bell state. So there are four Bell states, phi plus, phi minus, psi plus, psi minus. And this state, the density operator corresponding to qubits in this state, takes this form. So this is the phi plus state with 1 over square root of 2. And so it's 0, 0 plus 1, 1. And you can play, on a piece of paper, but there is absolutely no way to write this state as just some 0 times something for a state for A and a a state for B and just to do the tensor product. It's just simply not possible. So this is an entangled state. So the question is, how can we produce these entangled states, which are resources for quantum information processing? And so if you want to do something with a physical system, no, you have to interact with that system necessarily. Okay, if you leave it on its own, no, nothing will happen. So, well, there will be some unitary evolution, but it's so we want to interact with the two qubits. So instead of having just two qubits, no, which form a closed quantum system, we will deal with an open quantum system. So what I mean by there is that in a way that I can choose, that I can design, no, I will interact with these two qubits, or these two qubits will interact with the outside world. So now there are different types of worlds that can interact with the qubits. And so let me review the different ways to generate entanglement, and you will see that then I will be able to classify these different ways according to the role of dissipation or of the environment. So the first environment that you can use is an electromagnetic field. And the electromagnetic field, maybe you have seen that, but it's really some external drive. So you can think about it as a plane wave, no? E to the I omega t, it has some frequency. You will generate, in fact, a rotation, no, by applying this field. It's a unitary operation. And if you choose correctly your time t during which you let this field interact with your two qubits, you can choose which rotation you do on your two qubit states. And so one example that you mentioned is that you can use this electromagnetic field, the external drive, to implement a CNOT gate. So this is a matrix, so if I write a matrix, I have to define the basis in which it is written. So this is a computational basis or canonical basis for two qubits. So you see it's two qubits in 0, 0, 0, 1, 1, 0, 1, 1. And what you see is that so when the first qubit is in state 0, nothing happens to the second qubit, its identity. But when the first qubit is in state 1, you exchange the state of the second qubit. So this is a quantum circuit that you also showed. So A is called the control qubit, B is called the target qubit. So, and this is a formal mathematical operation associated with the CNOT gate. So if control qubit A is 0, you see it's 0 plus the state of B, so B does not change. If it's A is 1, then it changes according to the calculation rules modulus 1. So if I take one example, so I start with my two qubits in state 0, 0, and I apply a Hadamard gate. A Hadamard, it's a single qubit operation, okay? So the role of the Hadamard is just to put one of the qubits into a coherent superposition, okay? So here it's qubit A, which is in a coherent superposition, but this state, as you see from this writing, is still separable, okay? But if you apply then the CNOT, you see that the state here, if I write it, it's 0, 0 plus 1, 1. So if I apply the CNOT, the 0, 0 does not change because qubit A is 0, so I keep 0. But then 1, 0, qubit A is in 1, so 0 transforms into 1. So I get 1, 1, and this is exactly the state 5 plus that I introduced before. So this is one way, you see, to generate the CNOT, you can apply this external drive. This was done experimentally already a long time ago, and here just to show you, this is an experiment which was done in the Shulkopf group in Yale, okay? And here you have the two qubits, A and B, and here are all the control lines, which are radio frequency lines, okay, with which they implement the unitary gate. So that's one option for the outside world. Another option is to put the two qubits in a single environment, okay, so this time it's really large, and it is at a very cold temperature, ideally the absolute zero temperature. And why is that a way to generate entanglement? It's because this was shown that every entangled state is the ground state of a given Hamiltonian. So if you want a given entangled state, okay, you know that there is a Hamiltonian that if you reach the ground state of this Hamiltonian, you will reach an entangled state. But the drawback, then you may think, but then that's super easy, no? I just created, I just engineer a certain Hamiltonian, I cool down. So, but there are two difficulties, no? First, to cool down to absolute zero, no, which is not easy and which costs a lot. Second point is that if you want some tricky entangled state, like an entangled state between 7 parties, including the quantum club members, then you see that your Hamiltonian can be super complex to engineer. No? And but this was done, and this is just okay for your own interest. But that's a paper where they implemented the so-called AKLT Hamiltonian, which is quite complex, no? But they could engineer it, and they could cool down to show entanglement. Yes.
About any entangled state or just maximal entangled states?
No, I think, okay, that's a good question. I will say, no, I think, I would say any entangled states. But because, okay, why I say so is that if you go to dimensions higher than 2, I'm not sure how to define maximally entangled states in all dimensions. So that's why I'm a bit careful. But I could check and come back to you. So here you see, before we used a single environment at a very low temperature. So you use dissipation, no? You use, you cool down a system. So that's a different way to use the outside world. Another way is like you let your system interact with your outside world, but you choose how it interacts and you choose what is the environment. So it's not just a thermal bath that typically we assume to be given for free in nature. You engineer your bath. No? So by engineering, it can be, for instance, many qubits, or it can be so it's reservoir engineering, no? And experimentally they can do that quite efficiently. And for instance, this was done, no, in for instance those experiments where you have dissipation, so something leaks out of your system, but in a controlled way, such that in fact it drives your system into a desired state. Okay, so this is called reservoir engineering, bath engineering. So now, if I summarize what I told you, but I classify these different ways according to the role of the environment. I have these 3 categories. So the first one, when I use external drives, dissipation is clearly detrimental. And that's why they do all what they can do, okay, to isolate the system, to have no losses, no noise, and that's why it was a lot of engineering. So dissipation is detrimental, and because you implement unitary operations, then it means that it's lots of external control, okay, for the drives. Then there is this case, dissipation, it can be exploited, so it's not detrimental, but it's dissipation with a single bath at equilibrium. And so if you want to reach something useful, you have to go to 0 temperature, which is challenging. And here you have to engineer very complex Hamiltonian. And finally, the third one, it's engineered dissipation. So this is useful, but again, it needs lots of external control because you have to design on purpose your bath, your couplings, and so on. Okay? So the question, I did not appear. I know. So if I take my IBM chip, no, that I showed you at the beginning, the 3 different ways of generating entanglement can be shown like this. So external drive, this is good. And in fact, you can also think about what is useful, what is not useful in terms of your ability to control the quantum degrees of freedom of your system. So typically, you see when you have a finite number of degrees of freedom, just the 2 qubit states, then it's easy, so you can really manipulate quantum information. For an engineered bus, it also works because, in fact, you control the number of degrees of freedom that you manipulate, okay? But in general, a thermal bus at finite temperature, okay, it's described by a statistical distribution. You don't control the degrees of freedom, so you will lose your coherence properties, okay? So that's why typically for quantum information processing, thermal bus are really not good. And so, but at the same time, it will always be here, no? Because we don't live in a world at 0 temperature. So in fact, this is why some of fields that you may have heard about, NISQ, or developing detectors at the quantum standard limit, all these are very active fields, because the question of NISQ, which is near-term intermediate scale quantum computing, something like this. It means what can you do with a quantum computer that has a certain amount of noise, okay? So given that noise, what can you do? So this is motivated by the fact that you will always have some dissipations that you cannot control. But you can also ask another question. No? We know that dissipation that you do not control, so in the form of heat, no? When you control dissipation or when you control energy exchanges, it's more about work, no? Because you impose, no? It's a controlled form of energy exchange, whereas heat is better known as an uncontrolled form of energy exchange. But we know that heat is useful, no? For instance, in steam engines. So the question is, can we use a thermal machines, so using uncontrolled energy exchanges to generate entanglement? So I don't claim, that's important, I don't claim that this could be more efficient than what I presented you before. Intuitively, you can think that indeed it will be less efficient. But you see, it's a very fundamental question in the sense, given that dissipation will always be here, no? At least maybe we can understand what can we do with that dissipation? Can we reuse it for something useful in the context of quantum information manipulation? So this brings me to my second point. Do you have questions on the first part? So how can I see my quantum device as a machine? So you see, typically, so I have 2 qubits or a chip, okay, with quantum systems, and this I can consider. Okay, and this chip, or this qubit, as I told you, can be coupled to different types of environments, okay? So this chip, I can see it as a working thread of my machine, no? It is the system with which I will do some task. And all the outside worlds, which can be of different nature, I can see them as my resources or inputs, for the machine. And so then, of course, there can be some bias between 2 environments, bias in voltage, bias in temperature. So then this will drive some particle currents or heat currents through the system. So I have some thermodynamic forces, outside that drive currents through my system. And if it's a machine, it means that with my working thread subject to some inputs, I want to do something useful, because with a machine, we really have this idea of doing something useful. So what are the possible outputs? And these are classical outputs, that we also have these outputs with classical physical systems. We can do a heat engine, we can cool part of the system, or we can also manage heat, and this is, for instance, when we want to control the direction of heat or particle, no, a diode. A diode is what is a device that lets the current flows in one direction and blocks it in the other direction. So you can do the same with heat, no? And so, of course, this belongs a bit to all the field of either like big technologies, large technologies, or also nanotechnologies, but that you can describe classically, okay? But then the question is, okay, we are interested at what happens in the quantum world. So what can be quantum in this scheme? And in fact, there are plenty of possibilities. My resources can be quantum. So instead of considering just a thermal bath, okay, which is described by a statistical distribution, I can describe squeeze bath. So you may have not heard about squeeze bath, no, but these are like ensembles of particles which do host correlations, okay? So you can have entangled states, you can have a series of qubits in a coherent superposition. A possible resource can be also a quantum measurement, no? Because when you measure something, a quantum system, you will change it, no? You will act on it. So this can also be a resource. Of course, the working fluid can be quantum. So what are the main quantum properties, no? Quantum phase coherence, entanglement, no? Many body, I will say, and many body interactions, no? These are typically the thing you can play with.
Excuse me.
Yes?
Could you go over again what you meant by squeeze baths?
So a squeeze bath, okay, is an ensemble of particles which have correlations. And in fact, if you maybe in your lectures, no, you have seen coherent states in quantum optics, no? And a coherent state is really the most classical quantum state, or the most.
Can it relate it to like squeeze states or something? Can I form a correlation between a squeeze path and squeeze states?
No, so yeah, exactly. So a squeeze bath, no, for a coherent states, what I wanted to say is that if here you have the two quadrature, P, Q, no, a coherent state in the phase space has this form, no? Yeah. And a squeeze state is that you reduce the fluctuations in one direction, no, and you increase in the other direction. And this is exactly a squeeze bath will be a many-body system, no? And there are some collective effect which induces correlations, and this is a squeeze bath. Okay. So there have been experiments exploiting this type of resources to generate classical outputs. So for instance, this is an example of a heat engine made of a single ion, which is trapped by lasers, okay? And in the experiment, by playing with the lasers, they could change the energy of the ion. So this is doing work, okay? Because you change the energy of your quantum system. And they could simulate different temperature effective baths to really have the cycle, the 4-stroke cycle. I perform work, temperature, okay? And I close the cycle. So this was the idea of this single ion heat engine. In Singapore, they also did an experiment to demonstrate that you can cool down the cold system to a temperature which is colder than the bath to which it was initialized. Okay, and for this, the minimum number of qubits is 3. So then there have been many works a bit investigating the ultimate possibilities of this type of setups. And this, for instance, this is something that we did also here in Geneva with Nicolas Brunner and other colleagues. And this is an experiment that was done in the context of heat management, no? Where they took 2 superconductors, and this is a Josephson junction, okay? And in fact, because there is a magnetic flux enclosed by the squid, the ring, in fact, what they could show is that there is the current flowing through the junction, no? Depends on the temperature difference between the 2 parts of the ring and oscillates, no, with the quantum flux for magnetic field. And this is really due, because there are some quantum coherence, no? If the electrons and qubits were not coherent, no, it would not work. So these are examples. And an important question is like, if you look at thermal machines with some quantum properties, you get some output, no? But then it's always a very difficult question to answer, to know whether there is really a quantum advantage. So if I take a very efficient classical machine, can I get the same type of output? And you see, that's typically a question that we ask while doing research. But what is nice is that if we have a quantum thermal machines, we can also have quantum output. Okay, we are not restricted to classical outputs. And then the question whether there is an advantage to work in the quantum regime, it's solved, no? Because having a quantum output is something you cannot have with a steam engine. And what are quantum outputs? Quantum outputs are quantum correlated states. And here I show you 3 families of quantum correlated states. So these are GZ states, decay states or W states, and cluster states. So without entering, well, I can show you, but if you want, among the GZ states, no, so are states of the form, if you take 3 qubits, no, it's this type of states. Whereas a W state, no, is that you will share a single excitation among the 3 qubits. Okay, so this is the main difference. And this type of quantum states, they have different properties that makes them more interesting for metrology or for quantum repeaters, okay? And cluster states are many-body entangled states which are useful for quantum computing. Okay? So if you are able to produce such states, then clearly your machine is in the quantum regime and is useful. Okay, so these are really, just to mention and to connect now with ongoing research in that field, ongoing questions now concerned, for instance, what is the role of quantum fluctuations in those machines? Because you know that in the quantum regime, okay, your fluctuations, they don't go with 1/√ of n if you have many particles. No, you have some quantum effects. So can we exploit this? Does it allow to increase the efficiency of the machine? So all these are relevant questions. What are the role of interactions? So this relates to, for instance, the case when we have many body systems, and you have heard in these seminars now about people working on many body physics. Can we exploit, for instance, quantum phase transition to enhance the efficiency of the machine? And a general question is how to describe the dynamics of open quantum systems, because the dynamics for a closed quantum system, it's a unitary evolution, that's simple. But as soon as you let interact the system with something else, describing the dynamics unitarily, that's super complex, because you can have potentially many degrees of freedom. So you have to make assumptions, and you have regimes of validity for different types of evolution equations. And this is something that I discuss, for instance, in the course, in this advanced course on selected topics. But so what is nice now with that field is that there are some fundamental questions, but these are machines, no? So we really want to do something useful, no? So to trigger experiments, to care about scalability and sustainability. And this ultimately, no, is really a way to develop quantum technologies which are useful. And we are sure that quantum mechanics is an advantage. So after this, I can give you a concrete example and show you a bit how it works.
May I briefly ask
Yes.
about W state and GHZ state? Is it about working body state or source?
Is it about?
So you had 3 parts of your engine.
Yes.
Right? So what were the states about?
This was about producing quantum states. So to produce, but I will show you an example. For this, I will need 3 qubits. So my working fluid will be 3 qubits. And the idea is to start, for instance, with the 3 qubits in a separable state. And thanks to my resource, the currents, blah, blah, I can achieve one of these entangled states. Other questions? Okay, so let me take the simplest example, which is a 2-qubit machine. So here's the general setting. I have 2 qubits. They are described by this Hamiltonian, and they can interact. And the interaction Hamiltonian that I choose is known as a flip-flop type interaction Hamiltonian. And if maybe you're more familiar to this writing, okay, interaction Hamiltonian can also be written as, in terms of the Pauli matrices, okay, as the Pauli matrices, the product of sigma x for A, sigma x for B, sigma y for A, sigma y for B. Okay, and so in my basis of my 4 computational states, this Hamiltonian gives me just a G on the anti-diagonal. Okay, so it's diagonal. And so that's why it's a flip-flop, you see. Now I think you understand why it transforms 1, 0 into 0, 1. So what happens? If I couple each qubit to a thermal bath, but the 2 baths are at the same temperature, same chemical potential. So I have no bias, d'accord? Then in the weak coupling limit, and I will tell you why it is so. So weak coupling limit, it means, you see, you have to compare, well, when we define some regimes in physics, we compare energy scales, okay? So what are the typical energies that we can compare here? That's the interaction energy respect to the bare energy of the qubit. So when, and the coupling to the environment, okay? But so when I just consider the total Hamiltonian, if G is much smaller than E, then you see if I look at the total Hamiltonian and I diagonalize it, then the basis, the eigenbasis is the ground state, separable state, W occupied state, and the 2 Bell states. And you see that if G is much smaller than E, so this energy is large compared to 0. Okay, so my ground state is indeed the separable state. If G will be of the order of E, then you see that I have 2 possible ground states, no? Because this energy is close to 0, this one is also close to 0, so I could be in a separable state or in an entangled state. So then the situation is a bit different. But if I assume that G is much smaller than E, then even if I use, so my second option, to put my 2 qubits in a single environment and to cool down to 0, I will get a separable state. So this is not a valid way to generate quantum information in this system. Yes?
But in this Hamiltonian, is there the interaction with the...
No, not yet. Here I just look at the closed system of the 2 qubits. But I tell you, this is a way to see that if you put it in a single environment, it's useless. So what I do is to assume that the 2 baths are, for instance, at different temperature. And then I will have a current flowing from hot to cold. Here the intuition is correct, okay? And so I can wait until the steady state is reached. So steady state is the stationary regime, okay? So there will be a steady state heat current. And of course, creating entanglement is not magic, no? It's not just because I put two baths at different temperatures that I will get entanglement, otherwise we will know it, no? The trick here to get something interesting is to have, so this out of equilibrium situation plus some interaction Hamiltonian, which is a good one, okay? But what is nice is that for this system, the interaction Hamiltonian is super simple, no? And when I say simple, it's not only from a theoretical point of view, it's from an experimental point of view. These kind of interactions, experimentalists with many different platforms, NV centers, superconducting qubits, semi-conducting quantum dots, your favorite platform, they all know how to engineer it very easily. Okay, this is very standard. And so then, now on a theoretical point of view, when you have your Hamiltonian, the system interacts with the environment, you want to know the state of your system, rho. And why do you want to know the density operator? It's because then you can compute the concurrence and negativity that Anna introduced to know whether your state is entangled, okay? So you have to look for these evolution equations. There are many, depending on your favorite techniques, no, master equations, Heisenberg equations, green functions. I have, what, until 7, no? It's 3/4.
Yeah.
So just to give you an example how it works and the type of tools that we manipulate, I give you the example of the Lindblad master equation, which is valid for the weak coupling system to baths and with Markovian environments, which are environments which do not have a memory. So here I don't enter into details, but just to tell you that these equations are valid in a certain regime. So the evolution of the density operator of my system, no, this is the time derivative of the density operator for the system. Of course, it will have a term describing the unitary evolution of the system due to the Hamiltonian of the system, but it will have terms due to dissipation because we have the baths. So then there is a way to describe this. So to give you, to show you how it works, no, what you say is that my qubit, due to the presence of a bath that is described by its chemical potential temperature, it can acquire an excitation with a certain rate gamma plus, or it can lose one excitation with a rate gamma minus. And this gamma, this rate of acquiring or losing, no, depends on, in fact, the interaction strengths between system and bath. Okay, this is given by the Hamiltonian that I did not write here, but it's given by the Hamiltonian interaction Hamiltonian coupling strengths. And of course, it depends on the population of your bath. No, if your bath has some available excitation electron, it can tunnel into the system. If it does not have, it cannot. So it depends on the occupation probability of your bath, which is given by the Fermi distribution or Bose-Einstein distribution, depending whether you consider a bosonic bath or fermionic bath. You can have some. So with this description, the additional terms, they look like this, where you have so the probability to the rate of acquiring an excitation, of losing one. And here I don't explicit these operators, but you see the sigma plus is a raising operator for a qubit. Sigma minus is the lowering operator for a qubit. It's the similar, it's really similar, analog to A dagger for a Fock state and A for a Fock state. Okay. So here, these are the terms describing dissipation with the left bath. And if the two baths are independent, I just add the effect of the right bath. Okay. So these are things that we are able to write, to derive from the Hamiltonian description. And for instance, if we are interested in the steady state regime, so the stationary regime, we have to solve this first order differential equation equal to 0, okay? And you get some solution, and because of the shape of the interaction Hamiltonian, we have only these 6 elements which are non-zero, so the 4 population for my 4 computational states and 2 off-diagonal states. So now that I have this, I can compute concurrence, I can compute negativity and see whether I have entanglement. So this is what I show you here. So I fix the temperature of the cold bath, okay, and I vary the hot temperature. So on my x-axis, it's delta T, the difference between the two temperatures. And I show you the heat current and the concurrence. So heat current, you expect that as soon, it's the same with a classical system, no? As soon I have some temperature difference, I will have some heat current, okay? So this is the case for the two qubits being energy degenerate. And the concurrence, when I calculate it according to the formula you show, I also get a finite value for the concurrence. And maybe something that you did not emphasize a lot is that the concurrence is a measure, like so, and it only takes value between 0 and 1. And if it's 0, it's a separable state. If it's above 0, it has some entanglement. And if it's 1, it's a maximally entangled state. So it's a Bell state, okay? So here, what is important is that it's clearly different from 0, but it's small, no? And I will discuss that right after. If you have the two qubits which do not have the same energy gap, you reduce the heat current because the probability to tunnel through is lower, so the concurrence also reduces, and so on and so forth. So you see this type of works, they also, just to motivate also present research, no? If there is a one-to-one correspondence between some observable, transport observables, and measure for entanglement, maybe instead of doing the tomography, so instead of reconstructing, she showed this histogram plots, no? With the different things. So to experimentally, to be able to reconstruct that, no, they have to do 16 measurements, because for a 2x2 system, you have 16 elements in your density matrix, 4x4. So they have to perform 16 measurements, which are all combinations of the Pauli matrices. But if with some transport observables we can access the concurrence, then maybe by measuring the current or current fluctuations, you could certify the presence of entanglement. And this can be interesting under some experimental situations. And of course, something that is very interesting now is to, as I said, to look at current fluctuations, dissipation theorems, and the interplay with quantum states. But so the last point that I wanted to discuss is the fact that this value, it's not 0, okay, clearly, but it's very small, no, weirdly, because I told you it's 1 for maximally entangled state. So you see, we ask the questions whether, the general questions whether, is it the fact that we use thermal resources that set a fundamental limit on the type of entangled states that we can produce? So the question is really to know whether thermal resources do not allow you to achieve maximally entangled states. And to answer that question, what we did, so this was our initial setup, and what we did is, instead of considering 2 qubits, was to consider 2 qubits, so 3-level system. And here nothing is magic, no, again. So if I wait to the steady state, I will also get some entanglement, but it will be small, okay, because I did not change something special, because I also consider, like flip-flop type interactions between energy degenerate transition. So it's similar, okay, so it's not magic. But maybe you have heard about this in some quantum information course, no? You can what is called distillate entanglement. So by applying local operations, so LOCC operations, you can increase the type of entanglements that you have. And this is what we did by applying a filtering procedure. So this filtering consists in projecting our 2 qubits onto 2-qubit subspace. Okay, so we reduce the dimension of the Hilbert space. But this is done locally by projecting, you see, by applying a local projector onto this excited state or onto this ground state. So this is a local operation from the point of view of quantum information. If at the end you get your system is not constrained to that new subspace, we could show that the 2 qubits were in a separable state. If the 2 qubits were indeed in that subspace, we could show that we had an entangled state. So of course, entanglement, here you see it's negativity, the other measure. This having entanglement happens with a certain probability, okay? And it's the probability to pass. So that's why here I showed you the measure for entanglement as a function of success probability. And you see that we could get some entanglement with some probability, but we could also get 0.5 for negativity, corresponds to 1 for the concurrence, so it corresponds to maximally entangled state. So you get exactly 0.5 with probability 0, but you get something close to 0.5 with some finite probability. And we could even, then when you talk about entanglement, there are different, if you want, there is a hierarchy of quantum correlations. And so violating Bell inequalities is the strongest form of entanglement. Okay? So it's not because you have an entangled state that you will necessarily violate Bell inequalities. So we have to check whether, for instance, this kind of states could violate Bell inequalities, and this was done by using a criteria, which is known as the CHSH criteria. And if it's above 2, it violates Bell inequalities. So you see that this could happen with a success probability about 12%, which is non-negligible. So we could go to, we generalized a bit this idea to higher dimensional states. And for instance, so you see this scheme where you have 4 Q3 coupled to 4 different baths. You can choose which one is coupled to the cold one, which one you can choose, which one is coupled to cold, which one is coupled to hot. You can choose the subspace you project. And just to show you, so here we asked the question whether we could generate these interesting states, W, cluster state, GZ state. And the answer is yes, with a certain success probability. This is, for instance, the W states when one Q3 is coupled to 1 hot bath and the other 2 are coupled to cold baths. Or here it's the reverse, 2 hot baths, 1 cold bath. This is a cluster state. So we could compute this. And we could even ask, so the very general question, so that I mentioned before, are thermal resources a fundamental limitation to generate useful quantum correlations? And then you can ask so whether your entangled state is useful for achieving steering, teleportation, non-locality, which are all like advanced notion in quantum information, but which are something useful when you want to do quantum communication or quantum key distribution and so on. Okay, so this brings me to the end of my talk. So the motivation is really the following, that with quantum devices, we know that they will always be subject to dissipation. So one, I think, interesting question is what can we do with this dissipation to not only consider it as something detrimental, maybe it's still useful, okay? So this is the main motivation. The second one, which is an interesting and productive point of view, is to see these devices as quantum thermal machines, because then we have all the tools to compute efficiency, to investigate a bit how these devices work. But of course, we need to combine different fields, no? Quantum information theory, quantum thermodynamics, and open quantum systems theory mostly. But then you can ask questions towards quantum metrology, quantum sensing, and other fields. And so these are the perspectives, no? I think interesting fields or directions, and these are, okay, more my personal interest, no? That I just to share them with you. But it's about characterizing or understanding the link between fluctuations, quantum fluctuations, and dissipations. And yeah, then you can derive fundamental bounds, no, on the processes. To investigate topological properties of open quantum systems. So you may have heard about topology of Hamiltonian systems, but now Hamiltonian are Hermitian operator. If you look at an open quantum system, you can deal with non-Hermitian operators, and then you can ask, do they host topological properties? And of course, I have also this motivation to make useful devices. So for quantum sensing, quantum metrology, and so I'm a theorist, but I also work with many experimental colleagues. And so I'm happy to take questions, and I thank you for your attention.
Are there any questions?
Yes?
Can you go back to the slide
Which one? That
the one yeah, here. So how do you link the heat current to the energies of the two qubits?
Yeah, okay, so indeed I did not show you the formula, but so given a density operator, for instance the one in the steady state, if you have rho in the steady state, then within the formalism of master equations, you have a way to compute the current. And you see, I can explain it to you with this. You see, this is the unitary evolution, and this is what comes from the base to the system, with the plus. And gamma minus is what the system loses. So intuitively, you can understand that the current in, for instance, the left bus, will be given by all these operators which describe jumps of particles. So if you want, in fact, the particle, the particle current into the left bus, so it's an average, so you have to take the trace with respect to the steady state. This will be the current in the steady state. And then you have to do the sum of all, I can write it explicitly, but you want everything that connects with the left bus. So these are exactly these dissipators. And in fact, in this, here I did not say it, but these are super operators because they apply onto rho. And in fact, they describe quantum jumps. So it's really the fact that you can have this picture in mind that a particle jumps from the system to the bus, then it's minus, or it jumps from the bus to the system and it's a plus. And so for the current, you see, in a given bus, you have to add what comes in the bus and subtract what goes out, And so this is how you compute a particle flow. Then for the heat currents, you have to know each time that I have a particle tunneling from the system to the bus or vice versa, it also carries an energy. And this energy is given by its Hamiltonian. So in this simple case, you can, for instance, multiply here by h of the system. So the energy is the Hamiltonian, and you get the heat current. So that's a bit the idea behind.
But so the system is just two qubits entangled?
Yes.
So one of those qubits can leave?
Can
Can go to the bus? Like
No, so, okay, the qubits are fixed, no? What can go to the bass is one excitation on the qubit to the bass. Because if you think about, you can think about electrons or photons, no? What happens is that if I have electrons, you see my reservoir is a reservoir of electrons, okay? And what if I have my qubit which is in the ground state, it means I can have one electron tunneling from the bass to the system. And this is acquiring an excitation. But if it's already empty, if it's already filled, due to Pauli principle, if I do not consider the spin degrees of freedom, I cannot have another one, no? If I have different spins, it's okay, no? But so these are the type of physics.
How can I picture the paths experimentally? I mean,
Good question. So, for instance, the hot bath, no, we are collaborating with a group in the US, no, and they work with superconducting qubits, and the hot bath is a resistance. So you see, they put a resistance close to the qubit, which is a Transman qubit, a superconducting qubit. The resistance, there will be some noise, okay, which is some classical noise, thermal noise, which is called the Johnson-Nyquist noise. And then there is a connection between fluctuation between this noise and some effective temperature that the qubit can be described with. Okay, so for instance, a hot bath is a resistance, no, and then it's a classical system. For the cold bath, here it's a bit more tricky. If you want a bath at 0 temperature, you see, if it's at 0 temperature, the bath is frozen. So probably you can imagine that if the bath is frozen, nothing can go from the bath to the system. There can only be jumps from the system to the bath, okay? Because you have no available excitation from the bath. And so what they do experimentally is that they are able to make the probability for the system to acquire an excitation from the bath to be 0.
But the probability of jumping from the cold bath to the system back again, it shouldn't be 0, no?
No, it shouldn't be. But if you want to mimic a bath at 0 temperature, because you can never achieve an environment at 0 temperature exactly, you artificially cut this transition probability.
So I mean, it's so minimalistic that we can simply cut it off.
Yeah. Okay. Yeah. Yes. Yes.
Okay.
So it's about either they do have some physical systems which can play the role of the bath, or they engineer it or they mimic the effect.
Oh, by the way, I still don't understand the hot bath. Can you explain it in like classical terms or like?
So the hot bath, okay, if I talk about a bath, an environment, okay, you agree that from a classical point of view, it must be made of many particles in the thermodynamic limit so that I can describe it with some statistical distribution, okay? And so physically or experimentally, you must have a system which is large enough compared to your 2-qubit system to be able to be considered as a thermal bath. And so then it depends on your platform, no? How you implement this bath. But from a theoretical point of view, what is important is that you're allowed to describe it with a statistical distribution, either Bose-Einstein or Fermi-Dirac distribution.
Yep.
Yeah.
I was very curious about if I give you a state, how do you engineer a Hamiltonian for which this is the ground state?
So it's not you see, it's the question is not if you give me a state. The question is, okay, if I want. So I told you that every entangled state is a ground state of a Hamiltonian. So what you do is that you. So again, it's not magic, no? You have to gain some intuition and expertise, no, in manipulating Hamiltonian. But what happens is that you have Hamiltonian with different types of interaction, nearest neighbor, long range, and so on. And then you diagonalize it. You look for the ground state, and then you see whether the ground state is entangled or not. So it's very tricky, no? But this is a whole field of research, no, to investigate entanglement in many body systems. And maybe you had Dima Abanin, no, as a professor for some lectures, no, or.
He's gone already.
Okay, and but Luc Rademacher, he knows also a bit these things. So this is like a whole topics, no, in theoretical physics to investigate entanglement in many body systems, and of course to have the whole spectrum of very complex Hamiltonian. That's honestly almost impossible. So they focus on the ground state because then it's easier to calculate. Yeah.
And maybe I have the last one. When you consider qubits, so
yes.
Here, first of all, can you use this system in superconducting qubits? So in the second system, do you care about the lifetime of each level?
Yeah. So indeed. So this the qubit, no, they can be made with the superconducting qubits. So because you see, to make qubits, what they need experimentally is to have some anharmonic oscillator, no? Because if you have some harmonic oscillator, then every level is equally spaced, and then you have no way to say, I want to only work with the two lowest level, because you will touch your transition gap, no, is the same everywhere, so you will touch every transition. So what you look for is some anharmonic potential to get different transition energies. So with superconducting qubits, no, they have this. They have different ways to implement these anharmonic potentials, and depending on values of parameter, if I draw the potential, it will be, for instance, I don't know, it's a well like this, and I can control experimentally, for instance, the height of that well. Okay, and so maybe my first two levels. No, let me draw them here. No, maybe. My first two levels are here, no? So with that height, I can manipulate a qubit. But maybe if I increase that height, I can confine, you see, the third excited state. And then I can play with a qubit.
Yes, it should be smaller compared to.
Yeah, okay, so then the way the energy gaps changes, no, it's a yeah, depends.
But with the lifetime?
And about the lifetime, indeed, no. What happens is that you can take into account so finite coherence time or lifetime of your system. Depending on your theoretical framework, you do that in different ways. But for instance, here, it could be, you see, if you have a finite lifetime or finite coherence time, it means you can capture that with another dissipator, which captures finite coherence. But here, okay, in all these works, though, we were assuming that the lifetime is large enough compared to the other energy scales that set on the other time scales of the problem. And this is valid experimentally.
I was asking a bit from the different point of view because I don't remember exactly. I tried to find, but I didn't manage. So in trapped ions group at ETH, they also tried to implement the same experiment with qubits. And I guess there it was very important that the highest energy level was with the shorter lifetime than the second one. I don't remember why, but they should.
Than the second energy level?
Yeah, I don't remember why,
but I think it's okay, I don't know exactly this experiment, no, but for instance, if you want to manipulate a qubit, but you have your third excited level that you cannot completely ignore, okay, then if that third level has a lifetime which is much shorter than the first excited level, it means that soon it will not affect the dynamics of your system, no? So effectively, it can be justified to consider a qubit. So that's something you can think about, no? But I don't know if this was their motivation. And just, well, I don't know, but if, of course, no, if you're interested in that topic and so on, so we are always available. And we also always welcome master students, no? I forgot to tell it, but so it's important, no?
Thank you very much again, and we can go to the
You're welcome.